Hello everyone, welcome to the week 12 of the course. So in this week we will talk about various interesting aspects like interpretability and what do we need to do regarding the trustworthy and safe LLMs. So we will start the discussion in this lecture with the model interpretability. So we will talk about two different aspects about interpretability, probing and logic lens. So what do we mean by interpretability in general? So interpretability is a very vast topic in AI. So where we talk about the study of understanding why an AI system takes a particular decision. Okay. So what happens whenever AI system is making a prediction, giving a decision, an end user would believe it only if it is explained, right? I mean, why this particular decision has been taken. Now, for example, these systems can be used in various critical fields like medical field, legal field, where somebody's life may be at stake. I mean, depending on whatever output a language model is providing. Now, how do we know that the outputs or what is the actual decision that the system has taken? What is the actual flow of information or flow of reasoning that the system has been through to make this particular decision? So can we explain that? Can we analyze that, right? So there are two aspects to that. One is we analyze it from the model perspective, like what is going internally in the model, and second is how do we explain that in a term that is understandable by an end user. So and how that can help? I mean, if you can actually analyze and understand what the system is doing, it can even help in designing better systems that can do better performance and that are also human understandable. Now, traditionally interpretability had been used in very small models. Talk about Bayesian networks, linear regression, logistic regression. They were very, very small models, like 2-layer multi-layer perceptron with ReLU, very, very small models, and they have very small number of parameters, and you can do various interpretability on these models. But now when we are talking about deep models, especially large language models, now the problem at our hand is that how do we make sense of this huge model that we have at our disposal, right? I mean, starting from the embedding layer, self-attention, feed forward, and there are multiple layers of this. Finally, the unembedding layer. So what is going on inside each of these modules? Like what is going on inside self-attention and feed forward? Which of these is responsible for a certain behavior of the system? And you can even expand it to other things like multilingual, multimodal, which of this is more responsible for a particular language, right? How do we analyze that? Now, this is a very, very interesting and open field, right? I mean, so we will just discuss about certain efforts that people have been doing, researchers have been doing in this direction, but it's a pretty open field where one can easily think about new ideas and bring out innovations in which we can see how to, or we can actually look inside the large language model. So, we'll talk about various aspects. So, one of this that was very, very prominent and popular around when BERT came in was the probing method. What is probing task? So, I mean, so probing will be a classifier that is designed to predict some property from a pre-trained model's representation. So, you are talking about a pre-trained model that has been trained on a lot of data, and we talked about you can use BERT, GPT, T5, any of these pre-trained models, right? You can pre-train on a large data. Now, you want to see what are the interesting properties or whether this model has this property or not, right? Now, how do you know whether the contextual representation or just the pre-trained model weights contain certain information or not? So, whether we can predict some property from this representation without changing that. So, this is very important. So, we do not want to modify the representation, we do not want to fine tune the model for doing a specific task, but we want to see whether the pre-trained model itself can be used for doing a particular task. So what we will do, So, we have a pre-trained model, and given a sentence we can get the repetitions, right, of all the words and also for the entire sentence. So, whatever repetition this will produce, without fine tuning the model, can we use that to predict a particular linguistic property of the input text, right, and we will discuss about various works, what kind of properties do they try to predict, and that is probing, and you can even do it for doing interesting tasks, right. I'll give one example. So, this is what the approach would look like. So, you have a pre-trained model that is whose weights are frozen, right. Now, you pass a sentence. So, this is token 1, token n words of a sentence, and what will happen once you pass the sentence through this pre-trained model, you will get the contextual representations at the end, as we had discussed, right. So, we will get the representation for each of the token. Now, using these representations, or you are even allowed to take representations at multiple layers. So, but whatever this model provides without fine tuning the weights, I want to use them to perform a certain NLP task, certain linguistic task, like predict a linguistic property of the input. And we have to train this classifier, otherwise how would these representations map to a particular property, right. So, we train the classifier that okay, given these representations, now you predict a particular property, right. So, this is what we fine tune. This is anyway trained from scratch, this was not there. Now, what is the motivation behind this? The motivation is that if you can train this classifier, what does that mean? So, that means that information was somehow present in the representations of the data, right. Then only you could predict that property, right. So, if you are able to train the classifier to predict a property of the input text based on just the representations, what it means is that the property is encoded somewhere in the representation. But if you cannot predict certain linguistic property, that means that might not have been encoded properly in the representation, right. So, like this is one example of probing task, like do LLMs know the number of words in the input? Can you use the representation, like without cheating, without telling them the number of words in the token? Can you use a representation that is independent of the sentence length and try to predict the length of the sentence, right. So, let us say I have bird frozen, I just take the CLS representation of that is sentence representation. Now I can train a classifier on top of that from scratch. Now, can the classifier predict what is the number of tokens in the sentence, or can it predict the number of characters in the sentence, right. And if it can do that, means this encoding preserves the number of words somehow, right. Then only you can predict that. If it cannot preserve then the number of words in the sentence, you will not be able to predict by any classifier. So, this is an example of a probing task. Okay. Now, what were some of the interesting probing tasks? I will just give some details about two papers. So, this was the edge probing task. Okay. So, what is the idea? So, suppose you have a pre-trained encoder, right, and you feed a sentence, I eat strawberry ice cream. Now, so you have, so this dashed lines are all frozen parameters. So, you pass the sentence through pre-trained encoder, you get all the contextual representations. Now, using this, which is all frozen, you want to predict some property, like is there a relation between, or what is the relation between this eat and strawberry ice cream. So, eat and strawberry ice cream, what is the relation between them? And this you are doing for semantic role labeling. So, that means you will predict one of the arguments, right. This is argument 0, 1, 2, and this is the ground truth. So, how do you design the such probe? You will say, okay, I need to have a representation, because I have to predict between two spans, I need to get a representation for the span. Now, we had talked about various ways you can get this span representation, right. So, let us say I get a span representation for this and a span representation for this, right. Now, from these two span representations, I want to pass them through an MLP that can predict what is the semantic role, right, can predict one of the labels. So, I will train this classifier, right, and maybe I will have to train sentence span representation depending on what is the representation I am using. Is there some learning involved, or it is just an average or concatenation of the individual words. So, this is the probing, edge probing task. Now, in this paper they did it for various things, like a part of speech will not have an edge, will only predict for each word. So, The important thing about Disney is that it is a global brand. Now you have the word brand and you want to predict what is the part of speech, like noun in this case, right? And you have constituency, you have a span, you predict what is this span correspond to. It's a verb phrase, and this is now an edge task. Atmosphere is always fun, and this is a nominal subject relation, dependence relation. Like that, they had entities, semantic role labels, and so on, co-reference, including co-reference relations. So they try to predict various properties just from the representation without further fine tuning the model. They will only train the classifier on top of the representation. Now, what representation to use? Now that's why they went back to Elmo. Remember, in Elmo they had multi-layer bi-LSTMs, and for doing a task, what they were doing, they were taking in weighted average of representation that I get across multiple layers, right? And if you also remember, the idea was that the semantic tasks may need more weight from the higher layers, and syntactic tasks will need more weight from the lower layers. So they had a task specific weighted average of all the hidden states. So now they were thinking, okay, I mean, one can ask, maybe the information is already present in the word embeddings themselves, right? Why do you need to build a classifier from the final layer? So let's use a baseline way, that is a lexical baseline. So you simply use the learned subword embeddings from the full model and predict whatever linguistic property you want to predict. And the second, you would use the contextual vectors. That is, now how do you get the contextual vectors? I mean, they tried two things. For example, you have the subword embeddings from the 0th layer, the embedding layer, and you have the final representation from the final layer, right? So you have the subword embeddings and the top layer activations. You concatenate these two and use them to predict the property, right? And then they tried mixing. This was Elmo kind of mixing, where you take across layers the representations and you learn the weights in which you want to mix them, right? So linear combination of the layer activations, including embeddings. So it uses more information, strictly more information than concatenation, right? So this uses more than lexical, and this uses more than concatenation. And you learn what are the task specific scalar weights, similar to Elmo model. And then they try to analyze what is the performance of all these three competitive models for a particular task. So let's say, so these are the various things that they tried, and what you see, and as you may expect also, part of speech, lexical information itself gives a lot of idea. So if you just have the embeddings, it may encode some part of speech themselves. But if you add the final top layer embeddings, you get a boost in the performance. And similar things were seen across BERT base and BERT large. So this is okay, but now let's compare the next one, that is constituency, right? Immediately subwords do not do so well. So they only get a performance up to 68.4, while if you do the concatenation or mixing, you can get up to 86.7. So there is a huge gap now. And what they showed, like this is even better than Elmo model, so by 2.1% improvement, right? So now you can see which tasks can be done easily by embeddings, like entities. Embedding themselves can do by 90% accuracy, on which you get some boost by mixing. But say relation, like just 57 versus 82. So there is a huge boost by getting the combined information. And these findings they were finding were consistent, specifically if you go for larger model, the mixing always won. I mean, even in the smaller model, sometimes cat, sometimes mix, but in the larger model, mixing was always better, right? So that means what they found, that Elmo style scalar mixing instead of concatenation improves performance, right? And what it also tells that yes, you are encoding information so that you can probe from various layers. This is an interesting question though, that from which layer this information encoded. So from what layer I can extract this information? Is it in the embedding? That they saw that embedding does not encode everything. You need more from upper layers. Is it only in the top layer? Then you see that even the embedding and top layer together, if you concatenate, it does not always predict, right? I mean, if you mix information across layers, that's somehow better, right? And here specifically. So then there was another paper from the same authors that okay, now let's dig deeper and try to analyze the behavior of individual layers, like which layer may be much more helpful in doing a particular task or predicting a particular property in a probing mechanism. So what you are seeing here as the figure, so they again tried for similar things like part of speech tagging, constituency, dependency entities, and so on. And they did these experiments on BERT-LAS, which had 24 layers. So L is equal to 0 is the embedding layer, 24 is the top layer. So what you are seeing are the performance for just the embedding and by using the top layer. Okay. Now there is something else that you are seeing in this picture, that is they computed two things. What is the expected layer, right? That's what they wanted to come to, that around what layer do we have this processing, right? And what is the center of gravity. So we will discuss the definitions for each, but I mean, from seeing the picture you get some interesting trend that for part of speech the expected layer is much lower, like 3.3, roughly close to 3.4. Same for constituency, but if for relations this is much higher, like 9.4. And same goes with the center of gravity also, right? It keeps on increasing. It's highest for co-reference resolution, which is much more involved semantic task, right? Now, how do you really compute these quantities and what are the definitions for expected layer or center of gravity? So let's see. So they say, okay, so I am still doing the probing and I'll do the Elmo style scalar mixing of the weights. I'll mix the weights from embedding layer up to the 24th layer and get my final representation for the sentence. Now, how do you learn these weights? You will learn these weights with the probing classifier, right? So that it can extract information whichever is relevant for a particular linguistic property, and without adding a large number of parameters, right? I mean, you don't have, it's very small number of parameters that you are adding. And after you train the probing model, so you have the learned coefficients, and you use them to estimate what is the contribution for each layer, because the idea is that if a particular layer is more important, the classifier will learn to give a higher weight to the representation of that layer, right? So you will be able to estimate the contribution of different layers to that particular task, and you will know which layer had the highest contribution, right? Or maybe all layers had equal contribution. So you can quantify various things if you observe what are the scalar mixing weights across layers for individual tasks. So they defined two things. One was center of gravity. So what is center of gravity? They say, okay, anyway, I'm computing this information per layer. Now I know the layer on which this is the value. I'll take an expected value. This is the expected value where you assume this to be the probability, right? And because they are the mixing weights, they are like probability distribution. So you get an expected layer by using the probability distribution. That is your center of gravity, right? Now let's look back center of gravity, and this comes out to be, I mean, you don't see much distinction, but it starts from 11, goes up to say 15, 16, right? That's the center of gravity. So it seems information is being used across layers, but POS uses more information from the lower layers and relations, co-reference, etc., slightly higher layers. Now then they tried another method, that is expected layer. That is, let's see if I use information only up to layer L versus if I use information up to layer L plus 1, what is the gain, additional gain that I get from layer L. So this is a much more specific method, that is you will again do the mixing, scalar mixing, by only taking representation up to layer L. So you will start from embedding layer up to layer L, and then you will start from embedding up to layer L plus 1, right? And you will mix the information. So this is L minus 1 in this formula. So you have layer L and layer L minus 1, right? So you get the information. Now you see what is the additional gain you are getting by getting information from the layer L, right? This is the additional information that you have. So you compute the difference in the score, and this you can think of as the expected layer at which the probing model correctly labels an example wherever you get a high score. So again, now they take an expectation of this score, right? What is the delta that you get by this layer, right? And you take per layer, I mean, this is the expected value divided by this delta coefficients, because they were not like probabilities that that we had in the center of gravity. These can even be negative in some sense, but that happens very rarely. When you add more information, it goes negative. So they compute the expected value with this, right. So and this is where you see some nice differences, like in POS it seems you get a lot just by adding information from a nearby layer, but not so much when you add information from top layers. While in relations you need to add information from more top layers, they help much more. And using these values they also computed the KL divergence from the distribution that they are getting, right. The mixing weights are distributions and the uniform distribution, where let us say everything is given the same weight. And what they found, for example, like this is the POS example, and this is for expected layer, and you see first layer had a lot of weight, right. First layer, adding just the first layer had a lot of information, then second again gives some information and so on, but later on you do not get much information, even you get a drop sometime later, right. Similarly for constituency, first layer lot of information, so it is very similar behavior, little bit more, like one of this layer also helps. But now suppose we look at entity is very similar, the first layer is very important, right. Maybe the embeddings in themselves and just the one layer can be good enough for entities. But now if you look at coreference or semantic row labeling, adding the first layer does not help so much, right. You have to really go deeper, and then only you get better and better prediction. And even you see the KL divergence, so this looks a bit more uniform, like you have information across layers, so this is lower, but here this is like much more skewed distribution, so its KL divergence is much higher compared to uniform. So this is another way one can quantify, right, whether every layer is equally informative for a task or only some layers provide more information. Okay. Now from probe let us move to another interesting way in which we can understand why or interpret the interpretability of the model, right, and that is by the logic lens. Now, and also I mean, so this original idea came in a blog which was there in some papers, but this formally was brought out in this blog, logic lens, and then there was paper tuned lens which tried to further modify this idea, right, fine tune this idea. So what is the idea, right? I mean, logic lens is a technique by which you can encode the hidden states, decode the hidden states directly into vocabulary, right, and using the unembedding matrix. So that is the idea. You typically apply unembedding matrix to the last layer, right, the third layer of the last layer. But can you also apply this unembedding layer, which will project from the model dimension to the vocabulary dimension at any other layer in between? And if you do that, what do you gain from that? I mean, so something like, oh, from which layer I can extract that the model already started predicting the final token, right, like here. So from this layer itself, if you project the hidden state into the vocabulary dimension, you can predict the final word, right. So yeah, so like here, and this even like you have some layers for predicting best, suddenly it started predicting worst, and this continued, right. So that's again a very interesting interpretability technique. So what's the basic idea again? So so they started with a GPT-2 architecture, and they said what the architecture does. So you start from an embedding, word embedding, right. Now word embedding you project into 1600 dimension. So you have a one hot vector that gives you the 1600 dimension, the model dimension, and this you do multiple changes to this, right, through self attention, feed forward, multiple layers. Finally you end up with the final 1600 dimensions at the last layer. Then you apply the unembedding and you project into vocabulary. That is what happens. So that means we have a dictionary W that helps us in converting from the vocabulary space to the model dimension or the embedding space. So there is a vocabulary space, there is an embedding space, and you can convert from one to another using this matrix W. Now we use that at least twice, like very first embedding matrix, like converting one hot to the vectors, and the very last embedding vectors, right, converting the last representation to the hidden state. But what if we use the anyway middle representation, right? So, this is the third layer and this is the final 12th layer. So, what if I take the third layer representation and again apply this on embedding matrix and project into the vocabulary space? What would I get, right? Will I be able to predict what is the next word? So, and does that even make sense, right? And that is what they tried to find out in this blog, and the answer was yes. I mean, it was making sense, whatever were the predictions that they were able to identify. So, let us take an example from this blog. So, this is a sentence, specifically we train GPT-3 and so on, right. This was an autoregressive model. So, only a small portion is given, and what is being shown. So, when you pass the sentence, right, you will pass the sentence through embeddings. So, you have the embedding for specifically and so on, 1600 dimension embeddings. Now, these embeddings in each decoder layer, this is a GPT-2 model, each decoder layer, they will go through some changes and you will get the model dimension representations, right, in the layer 1, layer 2 and so on. Now, you can take any layer and you project it to the vocabulary using logit lens, and then you get the logits, and then you can even do softmax and calculate probability. So, in this picture you are just seeing the logits. So, the range is from 0 to 14 in this case. So, and you are plotting the logits, but you are not plotting the logits for the next real word. So, this is the word, the GPT may predict it, may not predict it, because you are feeding this word, this sentence, and you are getting the representation, right. The GPT may not predict it, that is an inference time behavior, right. So, you are simply saying what is the final word it is predicting, like here it is predicting based, while the next word is apostrophe or some semicolon, some colon, right. So, you are seeing the final representation of the GPT-3, GPT-2. From what layer I am starting to predict the same thing, like here this output, right, this from the last output, the comma, I am starting to predict from this layer itself. So, starting from here I am always predicting comma, right. But below that we were predicting something else like V, like specifically V, specifically targeted, but here you say specifically a comma. Now, you feed it back, I mean here you feed the ground truth and you predict again specifically, and does not make some sense, however, unlike, although, and then you start saying V, right, from certain layer, and this is what is the final prediction also, specifically V, and then you see again some things that do not make too much sense, but then you start saying found, we found, we simulated, we demonstrated, we show, and show is the final prediction, although it is not correct, the correct one is train, right. So, this was the train one, but it is okay, I mean this is also a valid construct, specifically we found, right. So, what in logit lens you are seeing that from which layer, if you project the representation to the vocabulary space, you get a similar word as the final layer, right. So, that is what the logit lens does. So, till now we saw what is the top one view, right, of each layer, but what about we find out the rank, right. So, there is always a last layer prediction of GPT-2 model. Now, what is its rank? So, its rank in the last layer is always 1, that is why we are predicting, right, in the greedy decoding way. But what is its rank in the just the previous layer? What is its rank in the 30th layer, 40th layer? So, in the, if it was random, it may be as bad as 50,257, right. That is the vocabulary, this is the vocabulary size of GPT-2, it cannot be beyond that, it has to be one of these ranks. So, wherever it is top 1, but where it may be top 10, top 100, top 1000, right. What is the rank and how does it evolve over the layers? So, they saw that, and you see interestingly, I mean if you look at the last few layers, the rank is, I mean always within top 10 in this particular example is that we are seeing, it always within top 10, right, the correct word. So, even if it was not put in the correct word at the top 1, it was there in top 10, but you see, I mean below that it starts going down. So, it becomes somewhere like 44, here you see even 1220 somewhere. In the beginning this is very bad, like 20,000, 9,000, right, but 14,000. but it slowly comes good, right, within 100, within top 10, and then then of course it has to be 1 because it's the last layer prediction, right. So question is from which layer you start getting the same prediction as you are making in the last layer, right. So you can visualize the top words, you can visualize the ranks of the final layer prediction, and you can even do QL divergence because even the rank one just see the top word, but the last layer also has a distribution, right. So we can take the distribution from the last layer logit lens. So here the last layer and some kth layer, and I apply logit lens at both the places. I have the distribution from the last layer, I can get from the kth layer what is the KL divergence between that, right. And this can give you much more continuous view. I mean, are you really going towards that probability? I mean, how is that KL divergence changing? Yes. And what they found again, I mean, this is the range from say 0 to 30, and actually at quite top layers you are very close to 0 always. I mean, you don't go to blue regions much till say even the like very beginning. So they are not very far. The distributions are not very far. Of course, they slowly come towards this, but they were hardly in this range except maybe the input embeddings, right, where this is the embedding of the previous word, not what you are predicting. So that's where they were bad, but apart from that they were going towards 0, right. So three ways you can see the top word, you can see the rank of top prediction, and you can even see the KL divergence of the distribution of top layer versus any of the layer. Now what tuned lens did, the later paper, so this was actually a paper, so they said okay, this worked on GPT-2 but does not work so well on other models. So what we can modify in this logit lens so that it works? So they said fine, so I will pass the embedding, I will get the representation across layers. Now my task is from this layer I want to predict the logits by applying the embedding. So they said okay, but why don't you even translate it first? So you first translate this to something that is close to the final layer, right. So you take the representations at this layer and you learn, I mean beforehand, what transformation I should do so that it starts resembling the final layer, right, and that you can easily do. We will see what is the method that they have used. And once you do that, I mean, then after the translation you apply the unembedding, because unembedding had been trained to be applied to the final layers, not to any of the previous layers, right. So you do some translation so that it starts looking close to this, its embedding space is similar, and then you apply the unembedding matrix. So that was the only change. So what is the translation that they tried? So what they did, so let's say we have the logit lens over HL, directly you apply this over HL. They say no, you first multiply with the matrix AL, so that you go into the embedding space of the final layer. Now AL, and you shift by BL. Now if let's say HL is of dimension H cross 1, so I want to anyway get H cross 1 to apply this unembedding. So this will be H cross H matrix, and this will be a bias, the shift H cross 1, and this AL BL is what they call as the translator for layer L, right. So you are translating this layer L to something that becomes easier for the unembedding matrix. But then you have some learnable parameters that you did not have in logit lens. So tuned lens has some tuning parameters, and these are AL BL. So how do you tune them? So what they say, okay, we have the final layer logits, right. So for a particular data I can get the final layer logits, and I can get the logits for the tuned lens by applying this AL and BL parameters. Now you take the KL divergence. So that was the idea. You take the KL divergence of the final layer. This is just for the final layer, and from the tuned lens distribution I get the probability distributions, and I take the KL divergence. Okay, and I want to minimize that, and this will help me in training what is the optimal value, what is the best value of this ALBL. And now you use that. So whenever you apply logit lens, before that you put this translation, and that gives you much better picture, and that's what they said. So like here this was giving some garbage tokens, but when you apply their method and go in the embedding space, this was much better. This output was much better from tuned lens. Okay. Now, we will continue this discussion for another 2 lectures. So, the next lecture we will see how this technique is applied in a multilingual setting, right. So, various papers that I have cited in the slides would be the reference for this lecture, and thank you.